we need to talk about the tools you'll need to learn C programming. And the basic tools you'll need, whatever your operating system is a compiler, a C compiler, and an editor. And the simpler editor is better, an editor that's a plain text editor. You can, of course, use something like Microsoft Word, provided that you store things in plain text. Microsoft Word is an intelligent editor. It adds all sorts of funky characters. A C compiler doesn't expect that, and so that would confuse it a lot. So if you're going to work on something like Windows, you can use typically a compiler like Notepad. Okay, what are the tools? A tool, for example, that's a C compiler that's freely available and generally can be installed on most any computer system, is the GNU compiler. The GNU compiler has as its command GCC, or of course the other major system you're likely to be on is Windows system, and there you can get very good tools directly from Microsoft, and they're probably the best tool would be a form of Visual Studios. Okay. Now, what I'm not going to do in this class is go into detail about different compilers, little nuances for the compiler, how to install the compiler. All of these things are required. In many cases, the install procedure is no more complicated than getting a package and just following the instructions that typically will install what you need. But if that's not your level of expertise and you're uncomfortable with that, you should get some help. So the presumption here is you have a C compiler and you have an editor. Again, I'm going to use a universal editor. It's freely available. It's sometimes called VI or VIM. As I said, an alternate editor for a Windows system might be Notepad. And what you'll see throughout this course is my home computer, which is a Mac, and I'll be using the Mac with its terminal window. Why the terminal window? Because that's a very simple programming environment. It's very vanilla. It's basically the Unix operating system. So some of you may even have a Unix operating system, either through your university or sitting on whatever box you have. And there are Unix operating systems that can sit under Windows, as well as the already installed one for a Macintosh. And what we will use is VI, and VI will be used to write code or data files. And the instructions that we need to use there are fairly simple, but again, it's not the point of the course, and so you should get comfortable with how to use a basic, simple text editor. Again, in this window, we will use the GNU compiler and the GNU command GCC to compile our code. And when you get an idea to write code for a particular problem or something you're interested in, or some test, I always say write the code first on paper. Paper and pencil, maybe I'm just old school, lets you think about it, and even what we call hand simulated. So not only do you write it, make sure visually it looks like what you think it is, it looks like a correct or syntactically correct C program, and then go through it, step through it, or at least a simple version of it, and see that it gives you the result you expect. You might even start with some sample program that you'll modify, and here's a very simple sample program. It's just int main void curly brace, return 0, semicolon. And when you're finished writing that code in an editor, so I've already written it on paper, I then go and open my editor. My editor command in this case would be VI. I would say VI of sample.c. And typically when I'm writing code for a C compiler, I have a suffix .c that indicates to the compiler that this is C code. And also if it sits in a folder or in a directory, I can recognize it as being source, what we call source C code. Then I'm going to actually make sure the program works as I thought. So we'll call in our GCC compiler. We'll see if there are any syntax errors. When we fix all the syntax errors, we can recompile. The fix is going to have to require use of the editor again. We keep running the program. We either get wrong answers, we go back here, fix, recompile, run, and then finally we should get a behavior we like. That's correct. And then in the GNU compiler, you'll see an output file automatically show up, which is your runtime executable code. You can think of that as machine code. And that file is by default a.out. And the problem with having a.out as your executable is anytime you use the C compiler, that a.out will be replaced if you have compiled a correct C program. So in order to avoid that, you can either change this by moving it to something recognizable, for example, sample exe, or you can do this from scratch by using the GNU command, -o means compile sample.c, and then the output should be in sample.exe. And now we're going to actually go over, and in the next segment, show me doing all this on my Macintosh environment. As promised in the last segment, we're in my directory. My prompt for my computer is iras air : and the local directory that I'm running in is called cprogram/week1. So here's where I developed some of the code that was being used in week 1 of this class. So let's look at that directory. The way we can see that directory, again, we're in terminal for a Macintosh, terminal window, which is basically running Unix. So I can use Unix commands. The Unix command ls shows me the files in that directory. So we see there's an a.out file, there's something called add2.exe, and then there are these .c files, which are source files, which are code, and then we can see something like miles.exe, circle.exe, add2.exe. So all of that are what I previously compiled into an executable, and I can, of course, execute them. Let's look at add2.exe. So in order to execute them, all I have to do is say add2.exe. It says input 2 floats. I do that, and I'm done. 4.3 and 6.8 is 11.1. Now, if I want to develop a program, let's say I want to change the input 2 floats program to an input 3 floats. Let me try doing that. So I'm going to have add3. I'm going to call it add3.c. vi add3.c. So this command means create a file called add3.c. Now, it's going to look very much like add2.c. So basically, and frequently the case is, I'm going to want to modify a pre-existing file. So I'll just read that file in. And these are all VI commands. And again, in this class, I'm not going to go through all of the VI commands or notepad commands. You're just going to have to get comfortable with using an editor. An editor is a critical tool for almost anything on a computer. And once you understand a little of it, you can get a tutorial that explains in detail the editing commands you need. So, okay. I mistitled that file, so I couldn't read it. There it is. Read in 2 floats. So here's a classic kind of thing. Let's change it to 3. So that was a CW that I printed, and that means change word. And I'm going to change the word to 3. Okay, today is not the 18th, it's the 19th. I'll change that. Again, I might have a sample program of some kind, and it's just always going to probably include standard I/O. And so I don't have to always be redoing my program. I have something standard. Now, indeed, if you go to an environment in Windows with something like an IDE, more elaborate IDE, like Visual Studios, it'll probably give you a basic template for starting such a program. So an integrated development environment like Visual Studios, once you get the hang of it, though, it's got so much stuff in it that can be intimidating, does give you a leg up on doing programs. It gives you a lot of additional assistance. So instead of float AB, we need a third. I'm going to just do an addition here. So I'm going to also have a C, comma. Okay. So little a says add at this place. It's a way to do an insert. And here I'm going to say input 3 floats. And I'm going to make an error here because I want to show you the whole cycle. So let's make an error. Instead of, I'll hit the wrong quote sign. So many places in a C program, we have to have matching braces, parentheses, all sorts of things have to match. Here I'm going to get a third float. I'm going to print the third float. I'm going to do an insert. That's another way to add immediately. So that'll be C equals %F. Oh, and here I'm going to also make a mistake. I'm not going to put C in. So it's expecting 3 values, but it's only going to display 2 values. What's going to happen there? Again, we're going to see how the compile edit cycle works. All right, so I'm done now, and I'm done, and I can exit, and I can do a colon, right? I can do a colon quit, and I can try to compile now. So I'm ready for the next phase, which is to call the compiler. I'm going to use this .o to say that I want that to be add3.exe if it works, and add3.c is my file to compile. Whoops, warning, missing terminal quote, invalid. And it even shows it. This is not being matched. So that's pretty good. And then it says error, makes a number of other errors because there's confusion about matching. So let me re-enter that editor. I used a shortcut. I just said exclamation mark V, which means use the previous editor command. Let's go and correct this error. I pointed it and even told me what line it was on. So I'm going to try and redo this, and I'm going to go ahead and also okay, 1 warning and 2 errors generated. It said a warning. There was more conversions than arguments. That's not a syntax error in itself. It's something where the compiler's intelligent enough to show that something did not make sense. But the warning didn't allow me, I believe, to still go ahead and build an executable. And this says input 3 floats. 3, 4.5, 6.6. And look what happened here. I got 3, 4.5, but C was shown as 0. But the right result happened, 6.6, and we ended up with a sum of 14.1. So if we had fixed the program based on that warning, and I'm going to go back and do that, we wouldn't have get that funky C equals 0, because C equals 0 was the initialized value of this float, but it wasn't changed by the scanf, because it was changed by the scanf, but it didn't show up in the printf, because here it said %f and there was nothing to read out of. So here we're going to now correct that. Okay, I think I corrected it. Let me recompile. Okay, no warnings, no errors, everything looks okay. Let's try the add 3 again. Input 3 floats, 1.1, 2.2, 3.3. That should be, what, 6.6, I hope. Sure enough. Done. So we've seen how we get syntax errors, how the compile cycle works, how we run, recompile, make our fixes, and finally get working executable. And indeed, if we go and look in the directory, there is add3.exe and our program. Okay, so this is my working environment. It may not be yours. You might have a different kind of Unix. This is under the Macintosh, but mostly Unix environments will look like this. Or you might have a totally different environment for Windows, and you'll have to use a different editor and probably a different compiler. Or you can import a GNU compiler within Windows and use a Windows terminal box as well. if you want to approximate this environment. Or you can, again, go and use Visual Studios and use one of its simpler project modes to get you here. Okay, so we just talked some about Dennis Ritchie. Let me put up his webpage from the Wikipedia. Okay. We can see Dennis, he was born in 1941, died 2011. Listed as an American computer scientist. He created the C programming language, and with a colleague, Ken Thompson, the Unix operating system. And that's his picture towards the end of his life. And as I mentioned before, he was awarded the Turing Award in '83, which is computer science's equivalent to the Nobel Prize, and he also got a Hamming Medal and a National Medal of Technology. And then another critical thing was he was the R in Kernighan and Ritchie, the C programming language, which was the original Bible for the language. So C was created by Dennis Ritchie. He was working with Ken Thompson at Bell Labs, and this was 1972. And some of the characteristics of the language that make it useful and powerful was it was small, as we'll see. The number of concepts you need to understand to fully learn C is much smaller than current languages. C++ is at least 3 times the size of this language when you use a metric like keywords. Keywords are critical to understanding language. They're reserved for special meanings. We'll talk explicitly about them shortly. It was low level. Low level is used when you need a great deal of efficiency and access to all the machine resources. So its job was to build an operating system, namely the Unix operating system. And that was the joint project of Thompson and Ritchie, where they won the Turing. And then the other thing it was highly efficient. It was easy to translate from C, sometimes C is called a portable assembler, into the actual machine code, regardless of what machine you were running on. C is sometimes referred to as a systems implementation language. And later, it got to be used as a general purpose language, but it was originally used to replace languages like B, its predecessor, and BCPL, which was B's predecessor, which were also being used to implement small operating systems. And they were also critically reliant on the design of Algol 60. Algol 60 was a language codified by an international group of computer scientists in 1960, right at the beginning of where there is computer science. And if you're interested in majoring in computer science or are a computer scientist, I highly recommend for the majors that you go back and look at Algol 60. Many of the concepts that we still are heavily using started with Algol 60. So when we examine C, we're going to see a first program. It was made famous by the Kernighan and Ritchie C programming language, the Bible. And indeed, it's one of the books I recommend, especially if you're a computer scientist, because it's somewhat sophisticated. And while my book, A Book on C, is more didactic, more tutorial, this is a very thin book for people who already understood programming. So it was written for people who knew other programming languages, just to expose them to the C language. And it was written beautifully, largely influenced by the first author, who was an excellent writer, Brian Kernighan. And in that language, in that first program, we see include standard io.h, which is a library for input-output. Then we see one of these keywords, int, includes a keyword. Includes a preprocessor keyword. Int main is always a function that we use. It's where the program begins, and then these brace pairs, well, those are parentheses. Then this is a curly brace. We sometimes indicate that that's the beginning of a piece of code. And then we have this function out of the standard library for I/O where it prints to the screen, printf, quote, this string, hello world. And we have this funny little \n, and that's a silent character. \n means instead of printing something, advance to a new line. And then we also have return 0, which says we're going to finish the program and a special value 0 is going to be indicated to the operating system, meaning everything has completed correctly. And then we have the closing brace. So one of the things you're going to be exposed to in programming is making sure you have matching braces, making sure you keep to your punctuation. There's matching parentheses. There's matching quotes. There's special, the semicolon is heavily used because the semicolon always indicates the end of a statement. So we'll have in our grammar, in the syntax for the language, things like punctuation, which are very important, special characters and punctuation, semicolon being most important, braces being incredibly important, and parentheses. And if we mismatch these, it's not like writing an essay. The compiler immediately basically issues an error and says it won't compile code. Now we're going to look at a program that has both input and output. So again, very critical. We frequently, as a user, we're used to it. Let's say in an app, we're always entering information, and somehow our program or app has to capture that information, and then it makes use of it in delivering a response or a computation. And this is going to be a very simple one that we all know about, which is how to compute the area of a circle. We're going to do that in terms of meters. So let's look at this code again. We're just getting used to how to write a simple C program, some of the elements of it, and later we're going to go into detail again about what each thing is and how it's constructed. So as before, there's our standard program comment, and it's really for readability, and in this case it's telling us this program is to be used for computing area of a circle. Standard I/O, the preprocessor command brings in both printf and now scanf, and scanf is a basic routine for doing input by default. In most cases, we will come from our keyboard. In the very old days, this could have come from a card deck or a paper tape. So it depends what you default. And in our case, standard input is defaulted to the computer keyboard. Here we see another directive. It's called a define directive. The define directive does an interesting thing. We have, and this is by convention, a preprocessor token. In this case, we'll call it pi for obvious reasons. Again, we want this to be documentation. We want to make the program readable. And we will define pi to 6 significant figures because that's what we get to store in the normal double, so it's 3.14159. Again, we introduce the program, which is main. We begin with what's called the open brace for a compound statement. And the first statement is a declaration statement in which we define area and radius. Area and radius are two identifiers. Identifiers can be ordinary words, unless they're keywords like double. So unless they're a keyword, you can make use of whatever you want to think about. And we initialize area to 0 and radius to 0, and we use 0.0 because that's a clear indicator that we're doing constants which are double. We could use 0, and that would be allowed. We then ask the user, please enter a radius. Otherwise, if we just didn't do anything and we had omitted this, and try omitting it, you'll see that your screen stops and you won't know what to do. So this is what we call a prompt. So it prompts the user to enter a radius, and this says enter the radius as a double, long float, and we need the special operator ampersand here. We'll explain that later, but for the moment, trust me, just use ampersand of whatever that variable is. We're going to explain that much later in detail in the course, because that's really a parameter that's the address of radius, and we'll have to understand things like address, memory, pointer to really understand what's going on. And here's our area calculation. Everybody should remember that from grade school or high school. Pi times radius times radius. We don't have a simple way to say square, so there isn't a notation like star star 2. So we use repeated multiplication, and then we print our answer. Return with 0. So let's make sure we can use that program. I've already compiled it. Now I'm going to execute it. So I compiled it into code, circle.exe. It says enter radius. Let's try the radius 1.0. Oh yes, 3.1459. Well, that makes sense. That's a simple test. When we go to debug programs, we want data for which we know the answer, and we want simple cases first. And we can ask for a more complicated case. Let's repeat that. So it's saying enter the radius again. Why don't we do 2.5? In this case, it's 19.634937. And that's correct as well. Okay, so that shows you how not only to do simple output, which we've studied in a few cases, but also simple input. And the little secret there is, outside of using a format string, where you want the input, you have a % with the appropriate format, in this case double, so it's LF. If it was an integer, it would be %D. And then we have to, instead of using the ordinary variable name, we have to use the address of that variable. Okay, so we need more practice with output. Output is a very important component of programming. We know the famous expression, garbage in, garbage out, and it wouldn't be useful in most cases to have programs that don't produce answers, so output is critical. So let's look at a program that's going to convert a marathon distance from miles and yards to kilometers. here's our program. The distance, marathon, and kilometers. Now again, that first part that I've just highlighted is a comment. A comment is just something that gets thrown away. So why do we have comments if it gets thrown away? Well, we need to make our code readable for a variety of reasons. First off, somebody needs to maintain the program. They have to understand what the program is being used for. What's the history of how the program got developed? So we typically like to put in when the program was last updated or coded and by who, and some overall comment as to the use of the program. Now, the first thing that actually shows up in the C code is what's called a preprocessor command. That's the sharp include. And inside the angle brackets, we see stdio.h. And the .h is an extension that means a header file. And that means that in this file, which will be included automatically with our program, so it's called preprocessor because it happens before the C code is compiled. So extra code gets added, and that code is the code that we're going to need for doing printf. Without it, the printf would be undeclared. Then we start the actual code, and that's with the keyword int, which means that the function called main, and almost always, in fact, in our beginning course, everything will always have a main. Main will be where the program executes from. That's understood by the C system. Void is another keyword meaning no arguments. So int is a keyword meaning that the program returns an integer. Void is a keyword that would, if it's used as a data type, means it's an undefined data type, or in this case, it means that the argument list is empty. The next thing we see is this brace. An open brace means begin the code. It's in programming languages, there are a lot of matching braces. We've already seen matching. We've seen the star asterisk match. We've seen the angle brackets match. We've seen the parentheses match. Very critical to getting syntax right is to make sure you don't improperly match braces. So for this brace, there's a closing brace, and this is called a compound statement. It's a series of statements that is the executable code here. We have two simple variables that are integer type, and this is called a declaration, and it's a declaration with initialization. So miles is initialized to 26, yards is initialized to 385. And a good programmer chooses identifier names. Miles and yards are identifiers. Why choose something like that rather than M and Y? M and Y might be okay, but it adds documentation at no cost. So the fact that we use an actual word like miles or yards gives the program more literacy, makes the program more literate. And then the result is going to be, again, a literate identifier, but this time of type double, and it's going to be kilometers. And then the formula is kilometers is assigned 1.609 times miles plus yards divided by 1760.0. I'm going to mention this because it's important and it will be re-emphasized later on. The reason that we didn't choose to use 1760 is that yards is an integer. This would be an integer, and if we did this without making this, in effect, a double constant, then this would have given rise to 0. We would have gotten the integer division of yards with 1760. And 385 over 1760, when they both are integer, is 0. So we could do this later. We'll learn that we can also use a cast. Another trick would have been to say 1.00 times yards divide by 1760. And what happens is there's an explicit conversion which takes the more extensive type and makes the whole expression be of that type. And then we have the print statement. And in the print statement, we first have the controlling format expression, which is a string. So again, you see matching quotes. At an earlier time, I left out one of these quotes, and you get a syntax error. So you should see what happens if you leave out one of the matches. You'll see you get very different kind and sometimes obscure syntax errors. But this says, print a new line, which means advance on the screen. A marathon is, this says, use a long float or double format. Print kilometers, period, and then 2 new lines. And then kilometers is in fact interpreted and printed as a long float. And then return 0 because we told you that int has a integer value, and so that returns 0, and mysteriously that returns 0 to the operating system. 0 being a code that the program ended correctly. So let's execute this. And indeed, we get a correct result that a marathon is 42.185969 kilometers. Okay, so study this program. It's a little more complicated than the previous program, but it gives you a lot of critical ideas, and we'll go into the various things that were talked about in later lectures in more detail. Okay. The next program we're going to look at is a program that converts from Fahrenheit to Celsius. That's degrees. So remember the Fahrenheit scale, for example, for ice, that's 32 degrees, but Celsius, which is a little more logical, it's in the meter system, and we go from 0, which is ice, to boiling water, which is 100, which in Fahrenheit would be 212. And it's a little hard to do that in your head, so we're going to just write a little program. And the reason we're going to do that program is that it illustrates a number of principles that we find in the C language, and indeed it's one of the early programs. A form of it is an early program in the great classic, the C programming language by Kernighan and Ritchie. And of course, remember, Ritchie is the inventor of the language, and there's a lot to learn. So if you're going to get serious about the C language, it's definitely a book you want to consider on your bookshelf. Now, as before, we're going to do input-output, and the character of the program is we're going to ask you to type in a Fahrenheit temperature, and then the conversion will be to a Celsius temperature. Int main void. Of course, main, by convention, is where we always start our programs. So a C program should always have a main, and technically its type, its return type, is integer. We're going to use, though if we wanted more scientific precision, we might use double, but in this case, we're going to use int as the basic type for Fahrenheit and Celsius. And then we're going to be polite on asking for data entry. Please enter your Fahrenheit as an integer. And notice again, for the moment, if you don't fully understand it, the scanf, which gets us input, we have a format that of %d, which is a format for integer, and then we use this fancy symbol called ampersand, and the ampersand means shove it in the address of Fahrenheit. We can't say Fahrenheit without the ampersand because Fahrenheit is a variable, and if we said Fahrenheit, we would look for the value in that variable. In this case, we want to look for the address of that variable. An address is a location in memory. And then here we do the computation. Celsius, it's Fahrenheit minus 32, and it's divided by 1.8, or equivalently, we could have multiplied by 5/9, and that's a conversion. When I say note conversion, that little comment means that this expression is actually going to be done as a double because the constant 1.8 is a literal double, even though this is an integer, and then this all gets done as a double and then gets reconverted to an integer. So there are what are called silent conversions going on, and we will have to understand them. They're often confusing for the beginner. Finally, we use a printf, and we have again, in that printf, we have two places where we're going to output integers. So we're going to output an integer, %d of Fahrenheit and %d of Celsius. Both will be integers, and return 0 is just the clear way, even though it could be omitted, that says we finished with main and everything is okay. Let's actually do a conversion. I think I already compiled it. So a dot out. Well, let me just clear the screen. Whoop. For example, 32. And that would be 32 Fahrenheit is 0 Celsius. So to see it a little better, I'm going to clear the entire screen. I will run my executable again. Let's see what happens if we do boiling Fahrenheit, boiling water. So that's 100. And if we were to do some random thing in the middle, currently where I'm sitting, it's about 92 degrees Fahrenheit. So Celsius, that would be 33. Okay, that program shows us how to use simple variables, how to compute simple expressions, and how to do input and output. And while it's not exactly the Kernighan and Ritchie program, it is very close. And if you go to Kernighan and Ritchie, what would be added in their version of the program is a little more sophisticated. And we're not ready for that. They do a while loop and print a whole table. Our next program is to compute the distance of a marathon in yards. So it's again a conversion program. Very similar to the program we did where we converted from Fahrenheit to Celsius. But we're going to see a few extra differences, and it's very worthwhile to practice on these programs because some of the very basic things you have to get down, and they easily trip you up later on if you try to do something more complicated. So the idea is we're going to take in miles and yards a marathon distance. You can see it to be 26 miles and 385 yards. And there's a formula. It's kilometers times roughly 1.6 times the miles plus the yards, and the yards is divided by 1760. And that's just a conversion formula we have to get you to kilometers. And then we'll print it. So indeed, if we run this program, I think I pre-compiled it already. And you see a marathon is 42.185969 kilometers. Now, the program we had just seen with Fahrenheit and Celsius, we kept all in integer. That's a rougher consideration. In this case, we wanted a more accurate answer for the marathon. Otherwise, if we had done it all in integer, we would get something like 42 kilometers. And that might be an interesting exercise to check, see what you would do if you did it all as an integer program. See if you would get 42. Now, let's explain some of the ideas we find in this program. This marathon program is taken from a book on C by myself and my co-author Al Kelly. It's one of the early programs, just like the Fahrenheit Celsius program is an early program in Koenig and Ritchie. And again, if you want to follow this course and you want a lot more detail and lots more exercises, a book on C is one place that you can get a lot more exposure. So there are some differences with the Fahrenheit to Celsius program. Let's look at what they might be. In that program, we had a declaration: int miles equals 26, comma, yards equals 385. That's a declaration with what's called an initializer. So each of those integer variables is given a value: 26 for miles, 385 for yards. Again, that type of statement is a declaration. In the program, we declare the variables we're going to use. We must name them. We want to pick names that are meaningful because that's good for the documentation of the program. It makes it easier to read and maintain, and easier for other people to use and modify for their own purposes. So miles and yards were identifiers. Int means that that was the data type those identifiers are allowed to use. And recall that on a normal machine, which is typically a 4-byte machine, where an integer is 4 bytes, you can get roughly plus and minus 2 billion. So if you go outside that range, something's going to go wrong. But if your program only needs the integers and plus and minus 2 billion, you'll be okay. Now, in some machines, you're allowed to go to long int, which might even be much larger. And there's even cases where you can go to long int. But if you need a very large integer range, you have to use special packages. The other key thing to look at in this program is an expression. And that expression, let me get this as full screen. That expression was kilometers is 1.609 times miles plus yards divided by 1760.0. It's very important that we used 0.0 rather than 1760. And this is one of the key things that can easily trip a non-C programmer up, and certainly a novice. So I didn't write out miles, I didn't write out yards, but I'm condensing this expression and adding parentheses. And those parentheses indicate the order in which the expressions are done. So the first thing that gets done is 7 divided by 1760. And the reason that we were careful about this to be a double is that if we had this as 1760, it would have been an integer divide. But when we make it 1760.0, it's a floating point divide. Now, 235 divided by 1760, if 1760 was an integer, the answer would be 0. But since it's a double, you get an appropriate to something like 6 significant figures expression for that value, a fraction. And we didn't want it 0. Now, once this expression is double, and we do this divide, and we get whatever we get, and then we add in miles, the second thing we've done is now add miles to that. And then finally, we multiply it by 1.609, and that's the third thing that gets done, and that gives us that answer of 42 kilometers and change. So it's very important in your expressions to know what domain you're in. By domain, I mean things like integer and double, because that's going to tell you what the arithmetic is being done in. And that arithmetic can affect the meaning of an operator like divide. Divide can be an integer divide if everything is integer, or it can be a floating point divide if one of the arguments is floating point, and then this answer ends up a double. Okay, so this example gives you a number of other ideas to go with the ideas from the Fahrenheit example. And let me give you a suggested exercise modify the program to input miles and yards. And then it could be a general conversion, much like the Fahrenheit to Celsius, to kilometers. You should be able to readily manage that, having looked at those two programs.